I think almost many participants already joined, so I can start. Oh. Yeah, so you can post your questions in the chat box if you have any query related to previous class or the class today. So let me open the chat box as well. Yeah. So good afternoon, everyone. And we were continuing the complexity classes, and Ajay shared, Ajay told that it's a vast subject, and I'm also learning a lot in this subject, and it has a lot of connections with the quantum computing. Although in syllabus, quantum part was not there, I will just touch various quantum complexity classes today towards end of the session. And we also need some detailed understanding, at least to some extent, on two particular topics. And the topics are, the first topic will start as NP hard and NP complete and NP completeness. So this is the topic for the first session. And in the second session, we'll start a new Turing machine set, probabilistic Turing machine. Under that, actually, we'll also discuss a little bit on BPP class and BQP class. So just as a summary, what is P versus NP? And then we'll go for certain more theorems and all. And I'll give a plenty of examples from real world problems so that you can connect this, because this is a theoretical theoretical computer science subject, but I tried based on my practical experience over years, tried to accumulate them with this subject, like blending with both practical and theory. So in theory, P class, just summarizing in one sentence, P class consists of all decision problems. Okay, I am writing decision problem. This is not a vague word. It has special meaning in complexity theory. There are various types of problem. For example, decision problem, searching problem. Okay, so this is a good class of problems, right? Decision problem is a wider class of problem. So in theory, P class that we studied last sessions consist of all decision problems which are solvable on a DTM. This is the important word, deterministic Turing machine in polynomial time. So in the first class, we learned about the notion of time complexity and space complexity, as well as the polynomial time complexity. Various lot of examples I have given in this particular category. So P class consists of all decision problem which are solvable on deterministic Turing machine in polynomial time. And when I say polynomial time, that means polynomial time with size of the problem. Size of the problem. So this size of the problem I have defined. What do you mean by size of the problem? Suppose you have certain problems, right? And towards end of the session today, we learn that if I have a quantum problem also, so how many number of qubits are required, right, to solve that problem? And even if I use that many number of qubits, say n number of qubits you want, right, to solve a problem, what is the time complexity of that algorithm, even if you take the inputs in n qubits, right? So there will be a different class for that. We'll define that particular class later on. So this is what P complexity means. Next is the NP complexity. NP consists of all decision problems whose positive solutions now I define the term positive solution, right? So earlier the P class problem I defined for the DTM, right? Discrete, a deterministic Turing machine. NP class of problem, typically we define the problems that is solvable in polynomial time, at least verifiable in polynomial time. But these are defining for the non-deterministic Turing machine. When I say this is non-deterministic Turing machine, that means there might be multiple solutions, right? And I have to pick up the positive solution, means yes solutions, right? So whose positive solutions are verifiable. I am not telling solvable. I'm telling about verifiable, because in the Sudoku example, in the last class we have seen the solution can be easily verifiable, but designing the solution is may not be polynomial time, right? So the definition is given in terms of verification in polynomial time. And also it is given the right information. If everything about the problem definition is clear, then only this is possible. So means whose solution can be found in polynomial time, uh, polynomial time using a non-deterministic Turing machine. In some textbook, it is written as NDTM, non-deterministic Turing machine. In short, we write as NTM. So of course, because it is deterministic decision problem and it is just a probabilistic case, right? Non-deterministic case, then we can easily say that this P class is a subset of NP, right? But whether NP, P equals to NP or not, this is a millennium question. This is not proven. Rather, many scientists say that NP not equals to P. There is a conjecture actually. Okay. But whether P equals to NP, it is not theoretically proven. Now we'll today we discuss certain more things, something called reduction and tractability. How to reduce a problem to certain category of problems, right? So I'll be sharing the notes. There are some more things in reduction and tractability theory. So to save time, I'm just skipping this part. This is also another important part, how to reduce a problem to another problem, okay? So for example, if there is a polynomial time reducible to B, that is written as A reducible in polynomial time to B, and it is possible if there exists a polynomial time computable function which is solvable in polynomial time. So there are certain definition, this kind of definition. I'll be just sharing that part with you. I'm just not just covering those parts. That will take a large amount of time. We'll be covering certain things that is called the Cook-Levin theorem. The theorem is only one sentence theorem, okay? Just a single sentence in this theorem, in this particular theorem, which is also basically related to this reduction principle. So before introducing this theorem, we need to understand also certain things. Okay, so for example, what is NP complete and NP hard, right? This is also important, and certain more definition like SAT problem, etc. So let's first define what is NP hard and NP complete. And then we'll come back to this definition, to this theorem, that how we can basically reduce to this kind of problem to a solvable problem. So I'm writing the formal definition first, then I'll give another definition, which is easy to remember, right? Because always if I say the easy definition first, there might be some computer science people who will feel that I'm giving a wrong definition. So let me first write the correct definition, and then to remember, we'll simplify the definition. So First is the NP hard. Let's define this, or NP hardness, sometimes we say. A problem B is NP hard if every problem A that belongs to NP satisfies that A is polynomial time reducible to B, that is, B is at least as hard as every problem in NP. Right. So yesterday we had seen only two particular categories. There is a bigger set which is basically NP, and within that there is a smaller set which is P, polynomial time solve. Basically, this is for the DTM and this is for the NTM, the deterministic Turing machine, and this is for all problems in the non-deterministic Turing machine problem. Right. Now these both P and NP are basically solvable to a within the polynomial class of algorithm. But there is a much bigger set which comes under EXP, like the exponential class of problem, because many problems in the world are exponential complexity problem. And because some of the problem we'll see that actually they are very hard within NP, and they are also expressed as exponential. And some of the problem we'll see they are not even, they may not be within NP, but they are as hard as NP, right? So we will be defining two particular class, and one of them is called the NP hard, which is basically within NP. That means that has a polynomial time description or verification, and there will be some problem which maybe in EXP, like exponential complexity, as well as in the polynomial time, but at least they are as tough as NP. Okay, so first of all, this class of problem, like the NP hardness problem, um, so in this particular case, B does not uh, need to be in NP itself. Okay, so this is an important point. Secondly, NP hard problems may be harder than NP. NP hard problems may be harder than NP. So suppose let's assume this is the polynomial the set of problems which can be solved in polynomial times, and outside this particular box, whatever problem exists that belongs to EXP or P space in general sense, right? And now I can find a reason, like say this is my particular P class, because this is for the DTM, the set of language or problems comes under the DTM, deterministic Turing machine. And this is for NP, for all the set of problems that's coming under the basically NTM, non-deterministic Turing machine, right? But both the P and NP are bounded within the polynomial set of problems, right? Now I can find a reason like this, right, which I called NP hard, that it may be some part of this particular set of problems, they belongs to P, but in general they may not be belongs to NP, because partly they can be also part of EXP, right? So NP hard not necessarily NP, only there is a intersection part that can be either I mean they can be NP, but in general they may not be always in NP, right? So I can find a particular intersection part, and this particular intersection is known as NP complete. So what is the definition of NP completeness? Now I can assure that NP completeness are harder problem. In fact, they are the hardest problem of NP, but they belongs to the polynomial like set of problems, right? That is the beauty of this NP complete problem, right? So let's define the NP complete first, and then we'll see plenty of examples, theorems, etc. So what is the NP completeness? A problem B is NP complete if number one, that B belongs to NP, means it is within the NP set. That means solution can be, this has a strong meaning. That means if I have a solution, then the solution is verifiable. I'm not saying solvable, I'm saying verifiable in polynomial time with input size. Okay. And secondly, this particular intersection B is NP hard. NP hard. Every problem is in NP reduces to B, right? NP hard. So NP complete problems are the hardest problem. So that means these are the hardest problem in NP. Means basically NTM set of problems, like non-deterministic Turing machine, the set of problems in NTM solvable in polynomial time. So that means I'm not saying that the NP completeness is the hardest globally, right? It is hardest within NP, but in like NP hard problem. Sorry, I wrote in hard. NP hard problem are the hardest problem in the global picture, right? And within the smaller picture, polynomial time complexity problem, NP complete are the hardest problem within NP. Okay. So that means NP complete problems are this set of problems. They are both NP and NP hard, right? So meaning that they are hardest problem inside the NP set. So we'll learn an example of this known as the SAT problem, satisfiability problem. This is an important problem. And for the NP, earlier I just told, I just told about the NP hard problem, and there is an example, and we'll study this example in much detail called the TSP problem or the troubling salesman problem. I'll also show an quantum definition of TSP problem, like troubling salesman problem, and how to solve that problem using the QAOA algorithm that is there, right? And you have already taken this particular algorithm for many applications, and I'll just discuss about the hardness of the algorithm. Okay. Right. So I just wrote two things, like the two examples. The first, let us study what is SAT problem. And this is one of the like core theoretical computer science area. And I'll just give a very brief, naive definition of this SAT problem. So the SAT problem, this is an acronym for Boolean satisfiability. Boolean satisfiability, or basically written as SAT, is one of the most fundamental problems in theoretical computer science. So the idea is, you are given a logical formula. Suppose you are given a logical formula of variables that can be either true or false. Okay. True means suppose it takes value of 1, or it takes value of 0. These are the only two possibilities, right, in Boolean algebra, right, in all classical logic, right? So can you assign, the question is, can you assign values, means either 1 or 0, to the variables so that the whole formula becomes true. So that's the logic, right? So let's take an example to understand this. So um suppose x1 or x2 and not x1 or x3, right? So these are the just notation. If you have forgotten, I'm just writing what this means. So there are three steps. First step is x or okay, x or x2. This is the or notation, right? And then we have and notation between the logic given like this. Then we have not x1 or x3, right? So not notation we have written as this, right? So let's take an assignment. So what we have to check that we have to basically pick up values for x1, x2, and x3. For what set of values of x1, x2, and x3, we'll get the entire logic is giving us value of 1. Means, of course, if there is and, that means this first part of this logic has to be 1. And second part of the logic also has to be 1. Then only 1 and 1, if they are the input of the AND gate, right? Then only you will have the output will be 1, right? So individually, I have to pick up value of x1 and x2. And similarly, I have to pick up the x3 such that the entire logic basically gives me 1. So let's take an assignment. So you may find multiple such assignments, and one of the assignments, suppose x1 equals to, we have chosen basically 0, x2 equals to say 1, and x3 equals to 0. Okay. If this is the assignment we choose, then the first part is basically 0 or logic 1, which is basically equals to 1, means or logic, if one of them is 1, then the output is 1, right? And in the third logic, this part, basically this particular part is 1 or 0. That means this is also equals to 1. And then between them, we have the logic and. So 1 and logic, that means I'll be getting 1, right? So this is my final output. So basically, I have to know that what is the set of values for xi that can take values of between 0 and 1 in such tuples, such that my formula f of xi or phi of xi should be equals to 1, true, right? So this is the problem. Okay. So now if no assignment works, then we say that if there is no such assignment, then we call that particular set of problems as unsat problem or unsatisfiability problem. Okay. So it is a this is also this is a particular problem comes under NP complete problem. And that means we can verify the solution is correct or not, but basically designing the solution will take time. Okay. So it is as hard as any problem in NP. So typically if we have n inputs, so that means we have 2 to the power n possible combinations of the inputs, right? Possible combinations. right? So that means it is basically some kind of exponential complexity with input x, with input n, right? So if the input is quite large, the number of possibilities it can take as input is quite large. That means it's is basically combinatorial space is huge, exponential, right? So that means it has an exponential growth of the problem. So it's a SAT problem, satisfiability problem with exponential growth. So computationally, of course, it is hard problem, right? So it has a lot of applications actually. Satisfiability problem it is used widely in VLSI design, VLSI circuit design, to basically verifying certain logics are possible or not with using a particular VLSI circuit. It is also used in cryptography to check certain cipher, certain text, etc., and whether a particular combination can be broken or not, software testing, etc., by giving the input output within the by giving the input and checking the output is matching, logical basically checking in the software, right? So there is something more um, with of this SAD, and let me define. There is something called CNF, and 3 SAT problem. So what is CNF and what is 3 SAT? These are just beautiful names. So what we have just done, there is a like formalization of that. So a CNF is conjunctive um, normal form, short form for CNF. Conjunctive normal form, or it's basically a formula. Formula is an and of clauses where each clause is or of libraries or literals. Literals. These literals can be variables or negations. Negations. So it is typically written as sum over basically AND gate, and or over variables u, j, I. Okay. So let us try to understand this practically, right? What the CNF means. Suppose you are designing a particular system, engineering system, right? And you have a set of inputs and set of equipments, right? So suppose this is your first part of the circuit, this is your second part of the device, this is the third part of the device, right? So, and you have given an input, right? And each such particular component of your bigger machine, right? They might have some multiple basically conditional equipment that if this situation is happened, then particularly this will be happening. So um, for example, it is summer, right? And we have air condition in our house, right? And air condition machine, the overall purpose is to making cooling effect, right? So refrigeration. So to make this cooling effect, right? Um, there are certain combination of blocks in the machine, right? Say this is the part 1 block, this is the part 2 block, and this is the part 3 block. Now, at least this block, it has to be one of the component of the first block has to work. One of the component of the second block has to be work. Another component of the third block has to be work. Then only if it is one, then only the overall functioning of the machine can happen. and I will be getting the cooling effect, right? Now, within any of the particular component, if there are multiple possible combinations, that means if the temperature is this much, then basically, or if this much amount of foods or commodities are kept within the fridge, let's switch on this particular device, right? If there is less parts, so only basically switch on this device. So any of this particular device 100, if this is the case, then only also this particular entire block will be actually basically functioning, right? So the overall combination of the engineering machine or the engineering system, it will be only act if the individual system, one of the individual system in a particular category is on and they are connected. That means there is a and operations between them. That means they have to be the collective basically operations in a particular part has to be one. So this particular formal definition in computer science is written as the CNF, right, or the conjunctive normal form. Okay, and one of that particular form is called a three-sat form, or also known as three CNF set, which is a specific NP complete problem requiring assignment assignment for a formula where every clauses has exactly three literals or variables. So the example is very simple. Suppose you have a logic x1 or negation x2 or x3. This is the first clause, and there is a second clause, either x1 or x2 or x4, right? If I have at least in each clause, this is a particular clause 1 and this is a clause 2, right? So clause 1 has to be satisfied 1. This entire logic has to be 1. This entire logic has to be 1. Then only I'll be getting a true answer for this, right? And we have to pick up values for what set of values in this particular combinations, because I have only 3 literals here. So when there are 3 such basically literals or variables, and the clauses are connected with the AND logic, we say this particular problem are 3-sat problem. Now 3-sat problem is foundationally in NP complete problem, because a larger variable problem we can always basically there are ways we can reduce them to 3-sat problem, right? So typically 2-sat problem is solvable. So general thinking is that 2-sat problems means if I can express a particular CNA problem as a 2-sat problem, so they are typically solvable in polynomial time. Polynomial time. But 3-sat problem generally they are solvable, or they requires order of 2 to the power n to solve by brute force. That means these are exponential time complexity solved by brute force. So sometimes my pen is creating problem. Brute force. So there is a question, why x4 is there? Okay, this can take x4, x5, whatever it is. Only you have 3 literals, right? So 1, 2, 3. Not necessarily in the second clause they have to be same. They can be very different. They can be any redundant variable. Okay, so x4 you can take x5 also. There is no problem. Only you have 3 inputs. in the first clause. In the second clause also you have three inputs. If there is a third clause, there is also another three inputs. This doesn't mean that in all the clause you have to be the same inputs. They can be very different inputs as well. That's why the complexity is coming, right? Now, I there is a theorem, and that particular theorem is called Cook-Levin theorem. So it was given in 1971. Actually, Cook gave the first theorem in 1971, and then basically Levin changed it a bit in 1973, most likely. So that's together it is written as Cook-Levin theorem, and it's just a one sentence theorem. Yes, there can be different components actually. The statement is Boolean satisfiability or the SAT problem. Let SAT problem be the language of all satisfiable CNF formula, then SAT is NP complete. Actually, there is a proof. I'm just keeping the proof. You can prove that SAT is a NP complete problem. What happens? There are many NP complete problems which are very difficult to solve, right? And we basically reduce that problem to a SAT problem. And because SAT problem is also NP complete, so if we solve the SAT problem, then we can basically equivalently we are solving the original problem, right? In computer science, many problem we convert it to Boolean problem, Boolean logic problem, where the universal logics are like and or not, right? In quantum computer also, we typically divide the problem in a way such that basically all operations we do using the single qubit gate and two qubit gate, right? Because you can ask, okay, why single qubit is not enough? Using the single qubit, you can do like certain rotation operation, etc. In basically SU2. But when you have multiple qubits, then only you can realize the interference and the entanglement phenomena, right? So, so these are like fundamental operation in quantum computer. I'll come to that point later. So, so basically we convert the problem in a way where it is easy to solve, right? Now I'll be drawing certain things. This may be helpful. And if you are interested to go in depth, so I'll be sharing the notes as well as you can basically look at the book. Okay. So let's talk about a language for all language, L, which belongs to NP class. Okay. And NP class, suppose I can reduce the problems of NP class to SAT problem. It's creating problem. Let me take another maybe. Suppose let's take for L belongs to NP, and I can basically convert the problem to a SAT problem, satisfiability problem, Boolean satisfiability problem. And this kind of satisfiability problem, basically there are major classes under this. Okay. No, Cat0 and Cat book is my own drafted book. This does not discuss much about the complexity theory. There are some like appendix on complexity theory, that is a very basic book. On computational complexity theory, on the first day, I referred to a MIT prof lecture series, Professor Sip sir from the math and CS department. And I prepared a detailed notes actually, I'll be sharing. Okay. Just today, let me just complete the lecture and I'll be sharing the notes. There are certain things. L is the language. Yes. So SAT actually, there are certain classes of things. First is the Hamiltonian path problem. And now you can connect some of this problem with your regular problems as well as the problem you look at in quantum computing. Basically, you look for this kind of problem. So Hamiltonian basically path problem, also known as Ham path problem. Okay. So also sometimes it is written as a D-Ham path problem or directed Hamiltonian path, which is basically understood using the directed graph. Basically, directed Hamiltonian problem. So I'm basically numbering this as 1, 2, 3 in this way. So one is the D-Ham problem. Another is basically 3-SAT problem. Because SAT is a bigger class of problems and okay. So let me write the professor name. Yeah, if you are interested about the theoretical details, so you can look to this lecture series, which is available at MIT OCW portal, or maybe you can get in YouTube. So that's details about the most of the P versus NP, this detailed class. But you may not find the examples that I'm giving. So basically, I have collected a huge number of research papers to prepare the lecture. And I'll be sharing the notes with the references. Okay, so it is not a single book thing. So there are a number of research references, paper references. So if you're interested, you can have a look. Okay. So one is the SAT, like NP problem, you can reduce it to Boolean logic problem, right? The satisfiability problem using CNF. And it may be a big number of variables may be there, but you basically reduce it to only 3 number of variables, right? In each clause, right? You check 3 clause, clause between 3 basically literals and then basically continue the logic. Now within the 3-SAT, I'll be doing the sub classification, and there are 2 more things. Let me first complete the first category. So the Hamiltonian path problem, basically there are 2 parts. One is the TSP problem, like the traveling salesman problem. And what is the traveling salesman problem is that find the shortest possible path, find the shortest possible path that visits each basically city once and returns to the origin. Okay, I'll discuss more on the TSP problem, traveling salesman problem, both from the classical aspect as well as from the quantum aspect. Then the another part is the Hamiltonian cycle. Hamiltonian cycle problem. So does there exist a cycle that visits every vertex of the graph, exactly once, and return to start. So this is a Hamiltonian cycle is one of the important like algorithm, right? In genome sequencing problem. I'll discuss later on a bit on the Hamiltonian cycle problem and how we solve the Hamiltonian cycle problem. So there are like algorithms to solve Hamiltonian basically cycle problems, such as the De Bruijn algorithm. So there is a lot of details. Those who are interested in the genome sequencing problem, they may look at. But just I'm touching from the complexity theoretic part. Now, another category. So under this SAT problem, let me draw maybe. There are, in fact, three of them I'll discuss. The first one is the integer programming. Um, no, I divided Hamiltonian path and Hamiltonian cycle. These are like Hamiltonian path is a broad category, okay? Within the Hamiltonian path problem, because every path may not be cycle, right? So the path which like there is a specific definition of what is cycle in graph theory, right? So for the cycle problem, there is a specific category called the Hamiltonian cycle problem, which is different. And there is something called the TSP problem, like traveling salesman problem within the Hamiltonian path problem. I'll discuss the TSP later in detail. So the problems, because I'll be discussing in detail, I'm not covering here. So I'll come to this problem later. Then the basically another category of SAT problems. One is the integer programming problem. So find the integer values or variables that satisfies linear constants. Linear constants. So those who like this is like there are like algorithm like integer linear programming, ILP, etc. Okay. Secondly, okay, I just saw this. I just kept it. You may not assume it as a subclass, but sometimes in some books it is written as theorems as a category. Okay, and they define as decide. Just one second. So decide whether a given logical statement is provable within a formal system. So this is quite generic. You may not basically put it as a separate class. There is something called codex problem. So there is a question whether Hamiltonian cycle and TSP are same or not. They seem to be same, closely related in fact, but they are not same. Okay. So typically cycle that visits every vertex exactly once and returns to the like start. And it is like for the specific to the graph problem. And it ignores the age, weight, etc. Whereas the traveling salesman problem, like we are basically interested to find the minimum cost cycle that visits every vertex exactly once. It's an optimization problem which uses the ages, weights, distances, cost, etc. And minimizes the total cost. So if you take TSP, you basically ignore the weights because set the all weights equals to 1. It becomes means if you put the weights of the basically edges in TSP, it becomes the Hamiltonian cycle in some way. Okay, so they are related, but they are not exactly the same thing. Hope it answers the question. Hmm. And the codex is that solve system of quadratic equation, system of quadratic equation, quadratic equation, equations typically over integers or Boolean values. So these are coming under the quadratics. For example, least square problem or the QC/QP problem, quadratic constant, quadratic optimizations problem, right? Problem. So this comes under the quadratics problem, which basically can also be mapped as a set problem. Okay. So this is a broad category under the set. Now, 3 set also has a number of thing. Okay. So, for example, it has two particular part. One is called the exact tone 3 set, exact tone 3 set. Um, so each clause has 3 literals and exactly one must be true. So one of the literals has to be true. So each clause has 3 literals, and exactly one must be true. So because in each clause you can take any variables, right? X1, X2, X3, or X2, X3, X4, or X2, X4, X5, right? But one has to be true among one of the among the literals. Then we say that particular problem is called a exact tone 3 set problem, which often used for basically subset sum algorithm. So given numbers, find the subset whose sum equals to a target value, right? So this kind of problem. And another category is called IND set problem. So here, this is basically short form for independent set problem. Independent set problem. What is this category of problem? Okay, so let me just discuss this part in a different place because it has some certain more categories. So IND set problem. So does there exist a set of k vertices such that every edge um, touches at least one of them. So this kind of independent set, they have also categories. So one is called the clique. So does there exist a graph that contains a subset of vertices where every pair is connected um, that means a complete subgraph. Subgraph of size k. So this set of problems basically comes under this category called clique. And there is one more category that is called the vertex cover algorithms or vertex cover set of algorithms. Vertex cover. So does there exist k vertices um, in every edge such that every edge touches at least one of them? So, and the example is called max cut basically. So I'll detail this max cut problem and TSP problem today. At least from the point of complexity theory. Okay. So we'll now come up with more and more examples. This is just a broad categorizations of many problems that is basically coming under set. It may be Hamiltonian path problem. Within that, it may be traveling salesman problem with weighted edges, or the Hamiltonian cycle problem where edges are just one. This can be three-side problem. This can be integer linear programming, theorems problems, or quadex problem. It can be IND set problem. It can be exactone three-side problems such as the subset sum. In the IND set, it can be either clique type of problem or vertex cover problem, right? So there are large categories of problems, and all these kind of problems belongs to the NP class, because in the previous class we have seen large categories of problem in polynomial class, right? Like the arithmetic multiplications, or the basically matrix vector multiplication, matrix multiplications, all these categories of problem, right? And now we have just categorized that if there is an NP problem, now NP problem belongs to the basically NTM categories, right? The non-deterministic, the Turing machine. So there, the solution can be exponentially difficult, but very verifiable in polynomial time, right? And we have seen the reduction to SAT problem and some certain categories. Okay, now let's come to the category. We'll talk about the examples. And first category will start with NP complete problem. NP complete problems. So I'll give one example, and then I'll give a basically I'll give a break of 5 minutes and I'll come back. So the first category is the TSP, traveling salesman problem. So the problem is given n cities and distances between them, between each pair, basically each pair of the cities, find shortest tour that visits every city exactly once and returns to the starting point. Yeah. So is there the decision problem is there a tour which has a length, so you put a threshold that the length is less equals to L, right? And this and we can check that the basically total distance basically in this particular case, sorry, total distance in this particular case is basically order of n, and basically this is sum of distance. Sum of distance is order of n, and we can check that the certificate. What is certificate? We discussed yes, like in the last class. Certification and the verification we can do. Those are basically in polynomial time, right? Because that's why it's a polynomial time algorithm. Yes. And this is verification in polynomial time n doesn't mean that the solution is in polynomial time. Okay. If we solve this problem using the brute force, basically that means the salesman without any prior knowledge just visits each and every pair and check. If we solve this using the brute force solution, it is n by 2, n minus 1 by 2 factorial. So that many possible routes are there for permutations of path, right? Permutation of cities. For example, if there are 20 cities, okay, that means there are 10 to the power 17 tours possible. So there is no polynomial time algorithm is known. What TSP problem? Okay. So it's an exponential. Basically, this problem is it belongs to the exponential category problem in terms of the solution, right? Um, so there are plenty of examples, right? Let's take one or two example under this category. So logistic, for example, um, suppose a particular track has to carry the LPG gas cylinders, right? And it has to travel multiple cities to basically deliver all the LPG cylinders. Now, if it basically carries with random paths, right, and here and there comes and goes and come back, so eventually there will be a lot of transportation cost, and hence the price of LPG will be rise, right? Because of the transportation cost will be very high. Can you find an algorithm in such a way that it has to travel 20 cities, right? As if wherever it starts, suppose it starts from Delhi, it has to come back to Delhi, but in a way that it travels the least possible path, right? Such that the total transportation cost is minimum. It has applications in PCB manufacturing, because in PCB actually you have this kind of basically one part is the metallic surface and another part is basically a non-conductive surface or insulating surface in PCB. So how many minimum number of holes you should do, right, such that you can basically design the basically connectivity of the path satisfying a particular logical basically combinations of the circuits, right? So basically, how much path you can connect is basically from there actually current will flow, right, within that. But if you create a lot of basically bulky connectivity, it can create many kinds of problem, heating problem, because of this. If you have a current, so basically it generates heat, right? As well as there will be a lot of like magnetic interference, right, because of the flow of current among multiple nearby nodes and all. Then one important problem that typically many quantum people are also doing is the genome sequencing problem. Genome sequencing problem. So where basically you have various kinds of right amino acids, basically combinations, like say for example ATT, TCG, TGG, or TCG, CGG, or ATA. So there are many particular choices of fragments of DNAs or the amino acids, right? And you need to basically connect them as a circle, right? Um, so basically, suppose you first connect the ATT, and then you have to find an overlap where it may be TCG or TGG. Next will be say GTC or something like that. So there are multiple possibilities, right? You have to pick up one of them, right? And it has to basically make a particular chain of such amino acids or fragmented DNA such that you prepare an entire genome, right? That basically signifies which kind of creatures it is, right? So whether it's a bacteria, it's a virus, what kind of virus, what kind of bacteria that is affecting the body, and can you? So there is a lot of study of this kind of problem, and this comes under the TSP problem, traveling salesman problem. Of course, that's why it's a TSP problem, right? TSP, we use the weights. If it is a Hamiltonian cycle problem, okay, there is also another sets of algorithm using the Hamiltonian cycle problem for this genome sequencing, but they are actually the weight are defined in a different way, actually, in binary encoding. So there are different like one hot encoding, um, cubo encoding. There are different types of encoding in quantum as well as classical for this kind of genome sequencing problem. Skipping this part, I'm not going in detail of this example. I started working on this problem with IIT Madras long back, but just 6 months I spent that I have very limited knowledge in that. So let's take a break of 5 minutes and then we'll come back with the problem. Second, basically problem is a knapsack problem. And after these two examples, there are plenty of examples, 4 or 5 examples are there. Okay, at least knapsack. Okay, let's leave the knapsack problem. This is every like we all know the knapsack problem. Let's go to the max cut problem. This may be beneficial. And then we can also discuss the drug interaction prediction problem. And then we'll directly go to the some of the um, in these classes, like the quantum classes, quantum complexity classes. So giving a break of 5 minutes and we'll come back. Yeah, I can come back to the knapsack problem. Okay. I mean, I have collected at least for NP complete 5, 6 categories of problem. For NP categories, there are NP hard category, there are several problems. I don't know like whether I'll be able to cover all of them or not, but yeah, I'll try. In test, actually, I gave very easy questions as I can remember. I always believe that um, like in terms of teaching or at least discussion, it should go as deep as possible. In terms of examination, question should be as simple as possible. Okay. Because marks doesn't mean a lot, but sometimes gives good grades, means happiness. That's it. We'll just start in 2 minutes. So 60. Okay. So um, Okay, I'm going slow, no problem. If I can't complete the things, I have class on Friday and Saturday on communication theory. So I take some part of that time to cover the complexity part there, quantum complexity part. So let's talk the knapsack problem then. So what is the problem? Given n items, with each with a weight, each with a weight wi belongs to certain natural number n, and each item or each item has a value of vi that is also, sorry, just got a call, just 1 second. So given n items and each item has a weight particular wi for the ith item, and and each item it has certain value vi belongs to the natural number n, and a knapsack with capacity w can we select items with total weight less than equals to w, and total value greater equals to v. So let me give an example for this particular case. Suppose you visited a city, say for example, you visited Rajasthan, okay, by flight, and your flight basically has a strict domestic flight, basically weight for your luggage be 15 kg, right? And now you want to bring a lot of items for your home, right? And each item may have some particular weight, 1 kg, 1.5 kg, 2 kg, lots of gifts, masalas, etc., right, from Rajasthan to your home. And then each particular item has a particular weight and they have a particular value v, right? And you want to maximize the weight, right? But it should be within 15 kg, but also it should satisfy that the maximum value is v, means you want to invest only 20,000 rupees for entire gifts and everything, right? So this is the knapsack problem. Now how much maximum number of item you can basically bring, right, such that you can give lots of gifts to many people, right? So this kind of problem. So what is the complexity of this particular problem? um Okay, so there may be different, lots of problems can be knapsack. You want to buy multiple things from Amazon, right? Or how many maximum items you can buy within 1 lakh rupees or something like that. So you can define knapsack problem for different examples, right? So if you solve this problem, there are algorithms, and one of the algorithms is called the dynamic programming. So if you solve the knapsack problem using dynamic programming, it solves basically in order of NW, right? Time, but W can be um, exponential in input size. Input size, that is the number of bits, for example, number of bits of W. So this is basically often it is called a pseudo. This kind of problem often it is known as a pseudo polynomial problem. Pseudo polynomial problem, because if your input size is quite less, it seems to be polynomial. But in general, if the input size is quite big, right? So this order of NW can become actually it basically it takes this basically form of a complex like exponential complexity order. So that means it is not a polynomial order algorithm, right? So there are plenty of examples for knapsack problem. So let me give 1, 2 examples. For example, portfolio selection. Portfolio selection. So you have some 1 lakh rupees you want to invest, or 10 lakh rupees you want to invest in fixed deposit, in SIP, systematic investment, in some trade, in many ways, right? How you can optimize the portfolio such that your profit is maximized, loss is minimized, and basically distributed among multiple platforms, right? That's the portfolio selection problem, which is an abstract problem basically. And then cargo loading problem, cargo or ship. Okay, cargo loading problem. How you can maximize certain commodities to a particular ship, cargo loading problem. The cloud resource allocation problem. Cloud resource allocation problem. um, Problem. Suppose a university buy cloud access from IBM, right? Quantum cloud access or classical cloud access from NVIDIA, for example. Then how a professor or the head of the institute can distribute maximally to the number of students and professors such that they get benefit out of it. And maybe he or she can set priorities for important research, etc. So that is also coming under the knapsack problem, right? So there was one crypto algorithm earlier days. The name of the crypto algorithm was Merkle-Hellman algorithm, crypto system. Because earlier days there was not much big computer, right? So which basically was designed using the knapsack principle. And now basically this crypto is not used. This is basically now broken. This can be easily broken by normal computer. Okay, so this particular cryptography algorithm earlier days people were using for, because that time there is small scale computer like basically calculator type things, or the floppy disk, etc. So where basically you could not do basically much computation if any say 6 digit basically pin code, right, etc. So this is an example of knapsack problem. And now let's come to the max cut. So what is the max cut problem? Given a graph G, which has two particular object, vertex and the edge, right? Vertices and edges, and threshold K, can we partition V into sets, S and S bar, such that at least k edges cross the partition. So there is a like weak tutorial in Qiskit, IBM Qiskit. Please have a look. You just type in Google max cut problem in Qiskit. Okay. There is a detailed tutorial of this using a lot of examples for quantum part of this max cut problem. TSP problem also there is a Qiskit algorithm in quantum. So you can have a look at how to solve TSP problem using quantum algorithm. Okay. So I'll just show that max cut problem, how it can be solved using a quantum computer, just a formulation of the problem. Okay. So what is the problem is that you have multiple nodes of a graph. It may be a complex network, right? So where from, like in this particular graph, say this is V1, V2, V3, vertex 3, vertex 4, vertex 5, vertex 6, and vertex 7. And there might be, say, edges 1, 2, 3, 4, and so on. So where is the optimal cut? Shall I cut from here? Shall I cut from here? Where from shall I cut such that actually the number of edges are maximized over the set S and S bar? Okay. So this is an important problem. First, let us discuss the complexity, then I'll show the quantum part of this. So typically, if we want to verify this algorithm, verification part, because verification part is basically polynomial order, right, for both P and NP problem. So hence the order here, it is just order of the mod E, means the number of edges, right, by counting the cross, by counting the cross edges across S and S bar. Now, it doesn't necessarily mean the solution is in polynomial time. Solution, if we solve this graph, basically the max cut or the graph problem, basically bipartite, even if you consider like the bipartite graph. So the brute force solution, if you just solve this problem using brute force technique, the total number of partition, is 2 to the power v. V is the number of vertex. And each partition, we check every basically edge. In each partition, we check every edge basically which crosses the card, crosses the card. So that is the order of E. Hence the total cost is order of E into 2 to the power V, right? So if you have E equals to V equals to N, total number of edges equals to vertex equals to the N, then this is equals to order of N 2 to the power N. So that means it's an exponential complexity, right? Um, Now, this is an important problem in VLSI design, network clustering. So there are lots of examples, like for example, the VLSI design. So you have to basically distribute the component across the basically PCB or across the silicon wafer, right? Such that the you can basically maximize the operations, right? You can do maximal operations, or you can minimize the cost of the overall production, etc. And network clustering problem, right? And then, so basically, if there is a terrain, right, and there are, even within the basically when we design the roads, right, there might be multiple communities, and you need to find at like which region of this particular entire big basically terrain region, right, where you should design the path such that the left path and the right part of the path, the people gets maximum benefits, right? It is not like you are just building the road for a one particular community, but there might be multiple communities or multiple like cluster of people in that particular region. So this max cut is useful there. Now let's take an example from physics side basically. So suppose your variables are like spin. That can take values of -1 and +1. Basically, say +1 spin or -1 spin, or a plus half spin or minus half spin. That's up to you. So now spin numbers we basically put for vertex, right? Now we write a particular cost function in this way: 1 minus gi gj by 2, and we say that if gi equals to gj, that means gi gj equals to 1. That means 1 times 1 is 1, minus 1 times minus 1 is also 1. That means the contribution is 0. We define in this way. Contribution is 0. And if gi not equals to gj, that means the spin has different, like opposite spins are there, right? That means gi times gj equals to -1, right? Then contribution equals to 1. For example, in the fermionic configurations, if not bosonic, like fermionic set, we just want to justify that the Pauli's exclusion principle, that only you can basically in a particular orbital you can basically put the opposite spin, right? So there basically you need to identify. Okay, you have basically in a molecular configurations you have, say for example, some 100 electrons, right? And you are designing like some molecular orbital, right? So for, like how you should, like, of course, like if in a particular atom set using the above principle, and there are certain quantum number principles following that, you can basically put in S, P, D, F particular order, right? And and accordingly, using Pauli's exclusion principle, you can put them, right, like opposite spin you can place in a particular orbital. Now if you do the molecular spin in particular molecular orbital, if you consider instead of atomic orbital, right? So you can have where you should put these two particular opposite spin, right? Or there may be, like, you can think in a chemistry way, but in general, this is the cost function, and we say that this particular logic will hold if they have the opposite spin, right? If that is the case, then we write the cost function C of z. Z is the spin variable for spin. That sum of all such I and j, and they can belongs to, say, some particular I and j can belongs to some bigger set E, right? And it is 1 minus gi gj by 2, right? And we want to maximize the cost function C of z. The problem is to maximize C of z, right? So if vertices are basically in different groups, they contributes to it means basically if vertices are in different groups, they contributes to cut the graph. Okay, so now if you just this is just simpler cost function based thing, like how you can basically maximize it, right? Now now if we just convert the variable gi to capital G, or we can write it sigma g in this way, right? So which is basically Pauli G operator. So Pauli G operator. So Pauli G operator is typically sigma g. We write it as 1 minus 1 0 0, right? And then this cost function is just convert from C of g, this particular cost function, to a cost function over variable, right? And that we write as HC. HC equals to sum over I comma j belongs to the set E 1 minus Gij by 2. So just I change the variable to matrices, Gij, they are operators, right? And instead of brute force, if we solve it brute force, we have seen the complexity, right? Instead of doing that, if we do using the QAOA algorithm, it is never a, if somebody claims that QAOA is a algorithm in polynomial time or something, that's a wrong answer. It is also belongs to the NP class, right? For the non-deterministic Turing machine class, right? And but it's a good heuristic. Heuristic, right? Means heuristic sometimes comes to a particular solution faster, right? So how to, I mean, so just let me give a very naive way to solve this problem. So earlier in the graph problem, we can start from anywhere, but in QA, what we do, we start from a superposition state, plus state of n qubit. So plus state, like it is like you are putting Hadamard gate to every circuit component, right? Q0, Q1, so on. So if you start the qubit from 0, right, gate 0 state, and you apply the Hadamard, so it become plus and it become plus. So this notation you write as plus 2 tensor product 2. Okay. So this we start up state, quantum state with plus state. And now we define two particular Hamiltonian. One is called the cost Hamiltonian. One is called the HC Hamiltonian or problem Hamiltonian, right? Because it is coming directly from the problem statement. Just give me a second. So like the pen is creating problem. So we start with the plus state, and we have two Hamiltonian. One is the HC Hamiltonian, which is basically problem Hamiltonian. And there is a mixing Hamiltonian, something called HM, mixing Hamiltonian, right? Now what I have to do, suppose I start from a point here, and here is my solution, right? And I don't know the exact path, how I can reach from start to end, right? Because at the end I have the solution, right? So what I do, I have a cost function, right? And I don't know whether the cost function is a perfect cost function or not. So I take two particular Hamiltonian path, HC and HM, and I mix them like HC plus HM with certain weight. Okay. Suppose I mix it with beta times, and I mix HC, sorry, I suppose I mix HC with gamma times and HM with beta times. I do a mixing of Hamiltonian. I make this kind of Hamiltonian, which is a parameterized Hamiltonian, where part of the Hamiltonian is coming from the problem statement, and part of the Hamiltonian I have the freedom to choose, right? And I basically combine them in a linear fashion such that I have a Hamiltonian there, capital H. Now what I do, if I apply this particular Hamiltonian, so I'll have a time evolution operator, and I will have a state that is psi gamma beta state, which is a parameterized with gamma and beta. And one Hamiltonian is minus I, time evolution operator is I beta HM coming from this mixing Hamiltonian time e to the power minus I gamma HC Hamiltonian coming from the problem Hamiltonian times the superposition state. That means I start a circuit which all have the superposition state, right? Then for the problem, that is the HC part, I design a unitary matrix basically for UC. And UC is basically e to the power minus IHC part gamma times, right? Um, and this HC part we have already defined. What is that? HC part was 1 minus Pauli G operator, right? By 2. And I apply another Hamiltonian, which is UM part, right? UM part is basically coming from the mixing Hamiltonian. Typically, these are sum of Pauli X operator, okay? Because there is a reason to do that. In adiabatic theory in thermodynamics, people typically exchange the head very optimally, like very subtle way, such that the total they vary the temperature in such a way that the variation of like exchange of heat is minimal, right? So gradually it reaches to the ground state very slowly. That is the objective, right? So if you do that, basically you come up with a quantum state here, and that quantum state, suppose it is psi alpha beta, right? Parameterized. Now you don't know which is the optimal alpha and beta for which you actually reached here. So you can reach here, you can reach here, but how to tune A and B such that I can reach from here to here or this way, or I can find a better direct way, right? So that's why actually there are classical loops to optimize this alpha and beta, and then basically you train the input. So this is the logic for QAOA. QAOA. So I'm not just teaching the QAOA algorithm. There is details you can find in the Qiskit or in some other lectures in QT5 or somewhere. But it is just a way how we define max cut problem, and then you solve it using a QAOA instead of the brute force. So if you solve in this way, and you can just see whether the question is, can I reduce the complexity order? Then the answer is no. It is still in exponential class of solution. But whether these heuristics give me faster solution because of the superpositions phenomena or not, you can check, right? The time complexity part. And of course, it's a heuristic. That means the solution you have generated, it is not the optimal solution. So there is another set of problem. So basically drug design problem or drug interaction problem. So if you have any question here, you may put the question in the chat box. Just take a glass of water. Now you can ask the question, if I am affected by some COVID virus, right? Some new virus. I pray to God that new virus should not come because we spend a very bad time in COVID, right? So we don't never expect. But the question is, if I want to design a drug for a particular attacks, right, or of a particular disease, why it takes huge amount of time? Why it's a difficult problem? Why everybody is trying to design a new drug using quantum computer, right? So what is the problem? Given a set of molecular features, given a set of molecular features, say the features are xi, which takes values of zeros and one, that means Boolean for I belongs to the set N. Okay, I may be 1, 2, 3, 4, such that. So you have a set of molecular features and interaction rules. Means who will interact with the other. Means if you design a drug which has the base component, base will not interact with base. It will only as interact with the acidic part of the other thing, right? So there is an interaction rule, what will actually do the chemical reactions with the other part and all, right? So there is an interaction rule. Typically, you can design the rules as Boolean clauses like the set problem. The question is, does there exist a molecular configuration satisfying all constraints? Right? So find x in 0, 1 n such that my function on x equals to 1. This is a set problem, right? So you get a solution, you take individual many such input like drug candidates, right? So in cancer T cell engineering, CAR T, so I'm just you can just see this example, CAR T cell engineering, how to actually prepare good candidate drugs. Okay, so you have a lot of possible drug candidates, right? And this may be the case that each candidate drug may not actually do chemically react with other, or they may not actually create an like effective solution. So there might be certain constraints which are feasible, or interacting drugs which does not. So you make a rule, you make certain clusters, and you prepare a logic between the clusters as AND logic, for example, such that the entire formulations that you have done using the certain possibilities of, say, class A candidates, and operation with class B candidates, and operation with class C candidate, and finally you come up with A, B, C, like A1, B2, and C3. This is the combinations, for example, and it is giving a solution, like it's a set problem. Now, drug design problems involving um, involving combinatorial libraries of compounds are routinely modeled as set problem. Or there is another way of defining problem which I am not covering, that is called constraint satisfaction problem. Satisfaction problem. So it is known as CSP problem. Okay, either of this way. Now, in whatever way you basically write the problem, what is the complexity to solve a drug design case? So in M clauses, for M clauses, that means you prepare M number of clusters, and each cluster, suppose it is an N set problem, that means there are N input variables. That means in each cluster you design N number of possible drugs, right? So T of N is order of M to the power N by brute force. Right? So usually it is solved by SAD solvers. However, all are exponential in general. So we typically, this kind of NP problem, NP complete problem, is very difficult to solve, and we design certain way to solve via SAD. but they are all exponential in general. You don't basically minimize this exponential problem to a polynomial order. They are still polynomial, sorry, they are still exponential, but bit faster. So there are certain algorithms to solve drug design classically, like DPLL. This is a method called the Davis Putnam Logiman Loveland. So these are the name of 4 scientists. I'm sorry if I pronounced wrongly. So DPLL solve this problem in order of 2 to the power n with exact solution. There is another algorithm called the CDCL algorithm, which is the full form is conflict driven clause learning. Conflict driven clause learning problem. It is also order of 2 to the power n. But there is, like, I am writing in order of 2 to the power n. There is when you actually write the complexity order, this may be bit more or less. Okay. But they are, of course, they are in the exponential order, but there may be slight difference among them. And this is treated as one of the gold standard in all drug companies, by drug companies like Cipla and all. There is another set of algorithm people have been studying called ILP, integer linear programming. This integer linear programming, they typically convert the Boolean constraints into linear inequalities. Okay, and solve using the and then basically ILP solves using there are ways like the branch and bound approach, or cutting planes approach. So it is also order of 2 to the power n. But these are some of the important methods in drug discovery to basically convert basically a NP complete problem to a set problem. So all these methods are basically converting a direct NP complete problem to a basically set problem. So at least it is from order of m into 2 to the power m to 2 to the power n. Some reductions are there. I mean, they are classically faster. Okay. There are many examples in NP hard, so I'm skipping the NP hard part. I'll take some more time for NP. So there are topics remaining like NP hard, co-NP. Okay, like examples for NP hard and co-NP. So in the co-NP, I'll show you one important example. Can you prove that whether can you find some values of A and B such that A square plus 2AB plus B square, whether this equation is correct or not? Can you find some A and B for which this equation is not valid? Okay. So this kind of problems comes under NP, co-NP. Instead of proving, you can disprove these equations, right? So basically complement way or language to basically prove a particular formula. Okay, NP hard and NP co-NP maybe we can discuss in the later class. So I'm giving just two particular definition, and maybe next day, if Professor Pillai sir allow me, I'll take a brief more on the complexity theory BPP class. So I'm remaining this part. Let me note it down. So that forward. Okay. So let me define one thing, something called a probabilistic Turing machine. And so I'm just starting this part from today. That is the quantum complexity theory. And this is outside syllabus. Okay. But this is important to know. To work with quantum computer, you need to understand what complexity category you are working on. Is it NP, it is P, or it is what, right? Otherwise, our entire the basically motivation of the QT series will be not fulfilled. So let me define something before starting the quantum complexity theory. I'm defining something called PTM, probabilistic Turing machine. Because in quantum, actually, the results we are getting, right, after initializing with certain qubits, applying certain number of quantum gates for quantum operations, you basically come up with a quantum a time evolved state, and you do quantum measurement. After doing the quantum measurement, whatever result we get, they are probabilistic in nature. That means I have to repeat the experiments. I have to see how many times a particular solution is repeated. And that probability gives me the sense of occurrence of an event, right? So for that, actually, computer science people, they defined a particular quantum complexity sets of basically classes. And in this direction, not only for the quantum part, but also for the probabilistic classical algorithm, there is something called a PTM, probabilistic Turing machine. A PTM is a Turing machine whose transition is randomized at each step. It can flip. So its transition is randomized, right? So earlier my transition function in Turing machine delta, uh, that was some sort of either 0 and 1, right? But in this particular case, it can be randomized, right? It can take a certain number of, it can be a random variable, in fact, right? So it can flip a fair coin and choose between two possible transaction, two possible transitions. The machine's behavior is therefore probability distribution a probability distribution, right? So at the end of the basically machine or language, you get a probability distribution, exactly what you get in the quantum, right? So you get a probability mass function of the like how many times a particular quantum computational basis is repeated, right? And like out of 1,000 quantum sorts or measurement, you get, suppose for example, 001 as a computational basis to be 100 times or 500 times, etc., right? So in a particular case, in the Bell experiment, suppose you have seen that the 00 component is repeated 500 times and 11 components repeated 500 times. 01 and 10 basically they do not occur, right? Theoretically. So you get the probability like this. So 00, 01, 10, and 1, 1. These are the four possible computational bases, and you have seen this 00 and 1, 1 to be almost 50% probability, right? And these rest are not counted. So this is the probability mass function for the Bell state, right? Because they are entangled pair. So a PTM accept input X with some probability a probabilistic Turing machine accepts input X with some probability of, just allow me 5 minutes more. I'm sorry. Just I'm just concluding this particular definition part. So m of x equals to es. So we want to basically, so we want this probability to be maximized, right? This probability close to 1 for yes logic, right? So there are two particular category under this PTM basically. One is called the BPP class. This is basically for classical particular language, classical complexity theory. So it's basically it's a language L. We say that if a language L in BPP, the full form of BPP is bounded error probabilistic. That means there is a, because it's probabilistic, that means there might be certain error, whether that error is bounded, right? And that bounded error probabilistic polynomial time algorithm. So earlier we have seen the like in case of TDM and NTM, we have seen we haven't seen this particular term. But in case of probabilistic Turing machine, we have unbounded error, probabilistic polynomial time algorithm. So this is the short form for BPP. We say a particular language is in BPP if there exists a PTM, probabilistic Turing machine, M running in polynomial time for every input x belongs to the language L, then probability of m of x equals to es. The probability has to be more than 2/3. And if x does not belongs to L, then probability of m x equals to es will be less than equals to 1/3. So the error probability cannot be reduced to, the error probability can be reduced to, it can be reduced to 2 to the power minus poly n, that is 1 by 2 to the power poly n, running large number of times, running this particular experiment. Because it's probabilistic, so you have to run this m experimented many times, right? And take a majority vote. Take a majority vote. Now you can ask me why this 2/3, why I say that a particular algorithm, probabilistic algorithm is good, or at least giving my solution if that particular solution is more than 66.67%, like 2/3 is the probability, right? So it's a convention, 2/3 and 1/3 is the convention. Because if I say just my solution is just better than 50%, it doesn't make sense, because 50%, 51% correct means there is a chance of 49% error in that particular solution. So people have chosen this particular convention 2/3 and 1/3. If the solution is at least good probabilistically more than 66.67%, 2/3 percent, then I say, okay, this is the correct logic, right, for that particular problem. So in general, this polynomial problem are a subset of BPP problem, and BPP problem is subset of T-space problem. This is the relation between this probabilistic and deterministic algorithm. So, so there is a, like, I'm concluding the classical part, and just after this, with this like PTM probabilistic Turing machine, maybe next day we'll see the BQP class. If time does not permit, so I will be sharing the notes for BQP. You can have a look. So thank you, everyone. I'm just concluding here, and if you have any questions, so I would like to take the questions. Yeah.
Thank you, Dr. Mustafizur. Participants, if you have any questions, please, you can place it in the chat. Dr. Mustafizur will be happy to answer. This part of the syllabus will be part of the quiz, so please try to understand.
Yes, sir. I will be sharing the notes with you today.
Yes.
And yeah, I mean, at least till this part, like the classical part, you may put the question. I have given sufficient question, 20 question, but you can pick any five easy questions for them so that they get.
Now, don't
Okay.
blame us.
Okay.
All questions, they will say all questions by Mustafa sir will be tough.
Sorry for that.
No, no
Yeah.
no problem. The standard is to be maintained. So, and hence you need to understand that by maybe losing few marks, you will remember those concepts. That is more important, and that is the effort. And yeah, yes, Bhavna ma'am, yeah, he takes a lot of extra efforts, and then of course gives us written notes also and printed notes also. So I
Sure.
think tomorrow he'll give you the printed notes.
Yeah,
Later
I
you will have
typically
that is as
prepare
a
this
part of the
kind of
textbook.
hand notes,
Right,
but I have also the LaTeX notes I'll be
right,
sharing
right.
there.
Later,
Yeah.
later notes, sir will be sharing.
Mm.
Devanshuji says that it is, what do you say? Printer ready, huh? Textbook ready, book ready notes, slides. Yes, sir. Prahalad sir, we will be sending the this thing. Yeah, we can do that. The slides will be shared, sir. Tomorrow, I think it will not be slides per se, but it will be, I think, like a PDF file having a lot of
Yeah, the
pages. Right?
PDF file itself has all the details. I'll be
Right.
sharing.
So the entire notes, it's not more of a slide, it is more of a notes. You can follow that, and it will be easy to remember and study. Uh,
Yes. Actually, these topics are like the complexity theory. It's a pure theory, like computational theory, core theory subject. But still, I tried to collect many research papers just to make it relevant to the quantum computing, relevant to the real world examples. Because otherwise, if you see more like those who just want to visit this with just books, especially non-CS people, they will stuck because it's a pure discrete mathematics and only like formal ways to defining things. So I was trying to see like how we can learn this subject from examples, right, in a easy way. Suppose there is a drug design problem, which complexity class it is, why it is tough problem. So it's like a motivation why we want to use quantum computer to solve problem faster that way.
There are two questions I think you can look at. Shall we use brute force applied to solve? That's one
Mhm.
question. And
You have
another
discussed
on
about.
dynamic portfolio optimization. Yeah, two questions.
Yes.
You can
Yeah.
answer.
When shall we use the brute force applied to solve? Brute force is like if you don't have any solution, you go for brute force. You search for every solution that is possible for a particular problem. That's when you don't have any known solution or algorithm for a particular problem, then we use the brute force. Second question is you have discussed about dynamic programming for portfolio optimization. How can we use this in machine learning model for the same? Okay, maybe you can search this problem because this is a bigger question and it will take time because dynamic programming, how it helps or it does not help, I also don't know. I have to see this thing. This is a very generic like research question. All of you take a lot of effort to give the best. Thank you so much. Thank you very much. Yeah.
Yes, so we'll take a break here. Thank you, sir. Thank you for sparing your valuable time. We have two more lectures.